Now we're starting Physical Chemistry, Chapter 15. We're doing Section 2 first. Now we're doing Statistical Mechanics. We're done with thermodynamics, kind of, sort of. And the kinetic molecular theory of gases. Statistical mechanics is the bridge connecting the microscopic viewpoint to the macroscopic viewpoint. The microscopic viewpoint, remember, would be like individual molecules or individual atoms. And then the macroscopic viewpoint is bulk matter. For now we're going to do a gas. The first macroscopic property that we're going to derive is the pressure of an ideal gas. Before we can do that, we first have to talk about one individual molecule in the system here. Let's say our molecule here is at point C. Now this is X, Y, and Z, but this is not position. This is velocity. So this would be the X component of velocity, this would be the Y component of velocity, and this would be the Z component of velocity. This O or 0 here would be the origin. Now remember, V without the line, this is speed, and V with the line over it, well, arrow actually, is velocity. So this line, let's see, this point B here, this is our point C projected down onto the XY plane. Now remember, the speed, it has to be greater than or equal to 0. Speed can't be less than 0. But velocity, it can be equal to 0, less than 0, or greater than 0. Now this line segment here, OC, or actually love the symbology, OC with a line over it, that's the length of this segment here. And this length segment here is our velocity. Except, well, OC, that'd be length, and I guess actually this would be speed too then, because the length would be, it'd be the length of the velocity. The speed, remember, is just the absolute value of the velocity anyway. So the length of this segment squared is equal to the speed squared. Now we can use the Pythagorean Theorem twice. We know that this line segment here, squared, is just equal to this VC squared plus OB squared. I didn't draw OB, but it's in here obviously. And likewise, finding OB with the Pythagorean Theorem, we know that's just Vx squared plus Vy squared. So using the Pythagorean Theorem, we know that the speed of when we're at point C is equal to Vz squared plus Vx squared plus Vy squared. Okay, and remember though, that since Vx, Vy, and Vz, these are the components of velocity, each one of those can be greater than 0 or equal to 0 or less than 0. Continuing on Physical Chemistry, Chapter 15, we're in Section 2. So this symbol here, this is called epsilon, and we're going to use it for energy, specifically the kinetic energy of motion. We're going to actually be interested in translational energy right now. Remember, translational energy is the energy due to changing position, movement. So we're going to use the subscript TR to remind us that it's translational energy. Now we know from physics that energy is just 1/2 mv squared. But since we have the three components, we're in 3 dimensions, we have 1/2 m times the x component of velocity squared, plus 1/2 times m times the y component of velocity squared, plus 1/2 times mass times the z component of velocity squared. Now remember, x, y, and z, those can be positive, negative, or 0, but if you square them, you're going to end up with positive numbers only. Now let's say that we want to have some time-dependent function. We're going to use capital F of t to show that this f is dependent on t. And this is just some sort of property or function. Actually, it's going to end up being force, but it'll work for anything really. So this notation here, the f in the brackets, greater than sign, less than sign, this is how we, this symbology for average value of force over time. So to find the average value of force over time, we just take 1/n times the sum from 1 to n of f of I. So f of I, remember, these are the observed values that we have. And then n is just the number of observations that we're going to make. So this is, empirical, actually taking measurements from a formula. Now, as n approaches infinity, I'm sure you know from calculus then that the distance between those measurements, in time remember, is going to approach 0. Therefore, this sigma becomes an integral. So what we're really interested in for an actual system then, the average force is equal to 1/10 time 2 minus time 1, so that's your delta t, times the integral from time 1 to time 2 of this function of time with respect to time, of course. You can call this equation 1 because we're going to refer back to it when we get some actual calculation for this function. Okay, continuing on our derivation of pressure. Now let's say we have a single atom inside of a box. Notice we have x coming up this way, positive y going to the left this time, and then z going up. So here's our box with y, x, and z. So this is the length of side y, the length of side x, and the length of side z. And we're going to be looking specifically at this left wall here. And we have a particle in here going towards the left right now. And it's we're going to call that I. This is one atom. And remember, we're using the cursive L for length. Now, since this wall is the left side here, its area is going to be the length of x times the length of y. No, length of z. The length of x times the length of z. And remember, we use lowercase a for acceleration. So the force on this wall is in the y direction. And so it's the force in the y component of force, because of particle I, is going to be equal to the mass of particle I, obviously, times the acceleration in the y, or the y component of acceleration of that particle I. And remember, acceleration is the derivative of velocity, or well, speed, with respect to time. So we have the force, the y component of force of particle I, is going to go to the mass of that particle times the derivative with respect to t of the y component of velocity of that particle. And of course, mass is a constant, so that can go in and out of the derivative. So we'll say the y component of force of particle I is going to be the derivative with respect to t of the mass times the y component of velocity of that particle I. Now remember, we use lowercase rho to mean linear momentum. And rho sub y, so the y component of momentum is going to be equal to the mass times the y component of velocity. So if we take the derivative of that, we get the derivative, or the differential of rho, the y component of rho, is equal to the force in the y component of force times the differential of time. Now if we take this equation and we integrate both sides with respect to time, then we're going to get, okay, the integral from t prime to t double prime of the differential of rho, the y component of it, is equal to the integral from t prime to t double prime of the y component of force with respect to time. Now we're talking about, while the particle is moving, there's not going to be any force. It's just coasting along by Newton's laws. But on the left side here, there's going to be a collision time. So all the force that happens during all this time is going to be happening only during this collision with the wall. So we're going to say the beginning of this collision is t prime, and the end of this collision is t double prime. So the total amount of time that it takes for the collision to occur is just going to be t double prime minus t prime. Continuing on what we were doing the previous slide, so we have the y component of momentum of I from t double prime minus the y component of yi at t prime is equal to the integral from t prime to t double prime of the y component of the force of particle I with respect to time. So these, from what we know about momentum, is just minus mv y component of I, and that's equal to our integral. Since there's two of these, then we have minus 2m y component of v of particle I is equal to the integral from t prime to t double prime of the y component of force with respect to time. Now remember, this quantity here, this integral of force with respect to time, this is called impulse. And since force is units of kilograms meters per second squared, and then time has units of seconds, one of the seconds is going to cancel out. So the units of this integral here is going to be just kilograms meters per second. Now impulse actually is a vector quantity, and it's kind of like average force, because we're taking force times time. Now remember, Newton's third law says that for any action, it's just the opposite of whatever action. So the force Yi is equal to minus Fwi. So Fyi, I already said, is the y component of the force because of particle I. So that would be this minus Fwi. This is the perpendicular force on the wall because of that collision with particle I. Okay, continuing on to derivation of pressure. So the integral we had before, but substituting in using Newton's third law, we have 2mvyi, notice the minus sign is gone because of that substitution we did, is equal to the integral from t1 to t2 of the force against the wall due to particle I with respect to time. Now remember this t1 to t2, this is a large time interval. So t1 to t2, it includes all the travel time and the collision time. So we have this 2mvyi is equal to the average force against the wall from particle I times the total time, temperature, time 2 minus time 1. Now remember, the total distance traveled all the way from the far wall to this left wall and back, delta y, is just the y component of the velocity times delta t. And delta t is obviously just t2 minus t1. So delta y is equal to 2ly, no, time 2 minus t1 is 2ly over velocity of y, the y component of velocity. Now remember, it's 2ly because we're making, the atom is making a round trip all the way from the far wall to this wall, hitting this wall, and back to the far wall again. So substituting that in gives us the average force against the wall from particle I is equal to 2 times the mass times the y component of velocity divided by the t2 minus t1. And so that's going to be equal to 2 times the mass times the y component of velocity divided by 2 times the length in the y of the box we're in, divided by the y component of velocity, divided by division, you know what I mean, puts it up on top. So we get m, y component of velocity of particle I squared, divided by the length in y. So this is the formula for average force against that wall just due to one molecule. Now to make clear what I'm talking about, the times here, so we have 4 times. We start out at t1 on the far wall. We have all this travel time where the force is 0. Then you have the actual collision where you're going to have a force on the particle in the wall. And that collision time is from t prime to t double prime. And then you have all this travel time back again to the far wall where the force here is going to be equal to 0. And then you've got the final t2 when you're back at the far wall. So this average force, remember, is against all of this time. Continuing on derivation of pressure, so we're going to use capital N for the number of gas molecules present in the box. So the average force against the wall, notice I got rid of the subscript I because it's not talking about just from one particle now, we're talking about from all the particles, or all the atoms, molecules, whatever, is going to be the sum of N, capital N, of that force against the wall from the particle I. So at this point, what we're obviously doing is assuming that all the gas molecules are identical. Now, if this isn't true, then we'd have to do a different sum for each type of molecule. But the end result is still going to be the same, so there's not really a point in doing it the hard way. So that's going to be equal to the sum of the mass times the y component of velocity squared divided by the length of the box in the y dimension. And this sum, remember, this could be for all the molecules in the box. So this is going to be the average force against the wall is going to be equal to mass divided by the length of the y. See how we pulled that out of the sum because it's constant. And then the sum of all molecules, the y component of that molecule squared. Now remember, the y component of any molecule squared, probably should have a I here, is going to be equal, we already showed before, is the sum of y divided, oh no, I see what I did, I rewrote this. Okay, so we're continuing on the derivation of pressure in a gas. So let's use capital N to denote the number of gas molecules that are within the box, our system. So we have the average force against the wall. Notice how I got rid of the subscript I, because we're not talking about the force due to one molecule. We're talking about the total force, or the total average force. So it's going to be the sum over all the molecules of the force against the wall of each I molecule. Now notice at this point what we're doing is we're assuming that all the I molecules are identical. If the molecules aren't identical, you're going to have to do a separate sum for each type. And there's no point in doing that the hard way right now. So that's going to be equal to the sum over all the molecules of the mass times the y component of the velocity squared divided by the length in the y. And this is for all molecules in the system. So the average force against the wall is going to pull out the constants here, m and the ly. So if the mass divided by the length of the box in the y direction, it's the sum of Vy squared. Now remember, the definition of the average Vyi squared is just going to be equal to the sum of all the Vyi squareds divided by the total number. So that's going to give us the force against the wall is going to be equal to the mass times the number of molecules divided by the length in the y times the average Vyi squared. So I just substituted in this sum here for this average. Now remember, the volume of the box is just the length in the y times the length in the z times the length in the x. And we know that A, capital A, is the area of the wall. Now remember, we're talking about the left side, so it's going to be the length of the x direction times the length in the y, or z direction. Now we know that pressure is just average force divided by area. So we're going to substitute in the average force against that wall. And the area, like I said, is the length in the x direction times the length in the z direction. So that's going to be equal to the mass times the number of molecules times the y component, average speed, times the length in the x times the length in the y times the length in the z, which is volume. Therefore, we have the mass of one molecule times the number of molecules times the average y component squared of velocity divided by volume. Hopefully you can tell the difference between my velocity, that y component velocity and volume here. Now remember, we're going to assume that the travel in all three directions is the same. So the average y component squared of velocity is equal to the average x component of velocity squared is equal to the average z component of velocity squared. Now, even in a room like this where there's gravity, that's a pretty good approximation. Because actually gravity is weak enough, you'd have to go out a couple decimal places before gravity becomes relevant at all. Okay, continuing on pressure derivation. So remember from the Pythagorean Theorem that the average speed squared is equal to the average x component of velocity squared plus the average y component of velocity squared plus the average z component of velocity squared. Now we can actually, because of the way they're calculated, we can combine these and say the average speed squared is equal to the average of the x component of velocity squared plus the y component of velocity squared plus the z component of velocity squared. And we showed before that these three directions are all the same, so we can just add these up and say, okay, that's equal to 3 times the average y component of speed or velocity squared. And then solving for that, we get average y component of velocity squared is equal to 1/3 the average speed squared. Of course, this will only give you a positive number, though. But, well, yeah, this would be positive, too. Okay, so we know that pressure then is going to be equal to mass times the number of molecules times the average speed squared, this is a lowercase v, divided by 3 times capital V for volume. Now we know that energy of translation is 1/2 mv squared, so the average energy of translation is going to be equal to 1/2 times the mass times the average speed squared. And so we know the average speed squared is going to be equal to 2 times the average energy of translation divided by the m. Remember, this m is the mass of your molecule in kilograms to get the units to work out. Alrighty, then continuing on pressure derivation then, so we have Now we have pressure is equal to 2 times the mass times the number of molecules times the average energy of translation divided by 3 times the mass times the volume. Obviously the masses are going to cancel out. So we're just left with 2/3 times the number of molecules divided by the volume times the average energy of translation. So we're going to multiply both sides by V to get PV over here. So we get PV is equal to 2/3 times the number of molecules times the average energy of translation. Now remember that we're going to use capital E for energy now, for total energy. So remember, this will be, average energy would be intensive. So we're going to take total energy, and that's going to be just the number of molecules times the average energy of translation. So ETR is equal to N times average ETR. Now remember, this other symbol, epsilon TR, that was first for one molecule. This is for the entire system, all the molecules together. So substituting that in, we get pressure times volume is equal to 2/3 times the number of molecules times the total energy of translation. And that is the end of section 2. We're in physical chemistry, chapter 15. We're beginning section 3 now. We're going to derive what temperature means. Now let's say we have two liquids here. One over here, and it's at temperature 1, and one over here at temperature 2. And they're in contact, so there's non-adiabatic. Energy can flow. Now we know at equilibrium, thermal equilibrium at least, temperature 1 is going to equal to temperature 2. We also know that at equilibrium, the average translational energy in system 1 is going to equal to the average translational energy in system 2. So if they're not in equilibrium, we know that thermal energy is going to flow from the hot one to the cold one until they do have the same temperature. This is how they reach thermal equilibrium. So what we know then is that the temperature is some function of the average energy of translation of the system. Now what this function is exactly depends on what choice we make for our temperature scale. So from before, we know PV is equal to 2/3 the total energy of translation. So if temperature is constant, then the total energy, this should be energy of translation, is constant. Now Boyle's law says that this product, pressure volume, is constant at constant temperature. So let's just define a constant K that's equal to 2/3 energy of translation. So then we can just say PV is equal to K at constant temperature. And this is Boyle's law. So that gives us, for those two systems on the previous slide, P1V1 is equal to P2V2. And we also know for an ideal gas that pressure volume is equal to nRT. Remember, lowercase n is the number of moles. So the total energy of translation is equal to 3/2 nRT. So we also know then that energy of translation is the total number of molecules times the average energy of translation. Now remember, n, the number of moles, is just the total number of molecules divided by Avogadro's number. So we can say that total number of molecules times the average energy of translation for one molecule is equal to 3/2 times the total number of molecules divided by Avogadro's number times the gas constant times the absolute temperature. Continuing on with temperature, so we know that the gas constant R divided by Avogadro's number will give us K, which is called Boltzmann's constant. Boltzmann's constant is equal to 1.38 times 10 to the negative 23 joules per Kelvin. And we know the average energy of translation is 3/2 times K times T. And so we know also, just rearranging this, R is equal to K times Avogadro's number. Now the average energy of translation, remember, with this epsilon, is the average translational energy for just one atom in 3D space. Now remember, for 3D space you have 3 degrees of freedom, x, y, and z. For each degree of freedom, you have 1/2 kT, how you can store energy. Now remember, we use the symbol U for the thermodynamic internal energy. Now for a monatomic gas, U is just going to be equal to the translational energy plus the electronic energy. For a monatomic gas, there won't be any vibrational energy and there won't be any rotational energy. So for U, we just have 3/2 nRT plus the energy from electronic levels. Continuing on, we're talking about temperature. So remember, the heat capacity at constant volume is the derivative of internal energy with respect to temperature, holding volume constant. So now we know that the heat capacity at constant volume is equal to 3/2 times N times R. So that the molar heat capacity at constant volume is just 3/2 R. Now since the electronic energy is constant, that's because, the electronic energy levels are constant at low to moderate temperature, up to about 3,000 Kelvin. That's why the internal energy is only going to be equal to the translational energy. That's why it's 3/2 R. Now the heat capacity at constant pressure, the molar heat capacity at constant pressure then, is 5/2 R, because the heat capacity at constant pressure minus the heat capacity at constant volume, molar for both of those, is equal to R. And that's for an ideal monotonic gas anyway. Now energy levels come in different sizes. The largest energy levels are the electronics, and within those there are vibrational energies, and then within those vibrational energies there are smaller rotational energies, and then within the rotational energies there are even smaller translational energies. Translational energies, they can change such small degree that it's effectively a continuum. They're continual. When we talk about quantum mechanics, get more into heat capacity, this will make more sense. So we know when we're talking about one molecule at a time, the average energy of translation is equal to 3/2 kT. Now, so we also know the average energy of translation is just equal to 1/2 mv squared, which therefore is equal, by transitivity of equality, to equal to 3/2 kT. So the average speed squared is equal to 3 kT over m. Notice the 2's canceled out. Now m, remember, lowercase m is the mass of one molecule, in kilograms though, to get the units to work out correctly. So if we take the square root of both sides, we get the square root of speed squared is equal to the square root of 3 kT over m. The square root of this squared, this is called root mean squared speed, and the symbol is going to be v, lowercase v for speed, and then RMS is short for root mean squared. So VRMS is equal to the square root of 3 kT over lowercase m. Now, careful though, this root mean squared speed is not equal to average speed. So the symbology of VRMS is not equal to this bracketed lowercase v. Now we know that Boltzmann constant over lowercase m, this lowercase m is equal to Avogadro's, R is equal to, what did I do? K is equal to R over NA. So that's what we did here. So this K over M is equal to R over Avogadro's number times this lowercase m. This Avogadro's number times this lowercase m is the molar mass in kilograms per mole. Okay, this is the last of section 3 here. So VR mass is the square root of 3 RT over capital M. Remember, capital M is in kilograms per mole. R is 8.314 joules per mole Kelvin, which works out in fundamental units as kilograms meter squared per second squared per mole Kelvin. So VRMS will be in meters per second. Now remember, M is molar mass. So MR is the molecular weight, which has no units because it's ratio to carbon-12. So the molar mass is just equal to the molecular weight times 1 gram per mole. Okay, continuing on physical chemistry, chapter 15. We are beginning section 4 now. Let's say we have the spherical shell. The spherical shell represents velocity space. So any point in the shell is a certain speed, or a certain velocity, actually. So we want to talk about the number of atoms in a spherical shell. Now, we've got this hollow layer here, this thin layer, and the thickness of this layer we're calling is dV. That's lowercase v for speed, remember. So that's the thickness of this shell. So we're talking now about the distribution of molecular speed. Maxwell asked this question: how many molecules have a speed in the range of v to v plus dv? In other words, how many molecules are within this layer here? The answer, we're going to call this number the differential of capital N lowercase v. So it's the differential, the number of molecules at speed v. Continuing on section 4, so the fraction of molecules traveling at a certain speed between v and v plus dv is going to be just this fraction here, the differential nv divided by the total n, and that's proportional to that dv, the thickness of the shell we showed you. So remember, this lowercase v is speed. So this ratio, it also depends on the actual speed. So to get rid of this proportionality constant and turn this into an equal sign, what we need is some sort of constant, or actually function. So what we're going to say then is that this differential of n of v divided by n is equal to capital G of v dv. This G of v, capital G, is going to take into account both the speed and the interval we're interested in. Now this G of v, this is what we call a distribution function, in this case for molecular speed, obviously. Now this can also be known as a probability density function. So those of you who have taken probability know what that means. So this fraction here that we're talking about, this differential of the number of molecules of speed v divided by the total number of molecules, is really a probability that the speed we're interested, or the speed of any molecule, is within the range of the speed we're interested in, from v to v plus dv. Continuing on, distribution of molecular speed. So this is the interval we're interested in, from speed 1 to speed 2. And we've divided into these equally spaced intervals. So if these are infinitely small, so each one of these intervals is the differential of speed, dv. Now we're going to use capital P lowercase r for probability for now. So that what we're trying to find is the probability that the speed that we're interested in is between v1 and v2. And this is a closed interval. It's the whole thing here. So what we're really trying to find then is the probability that the speed is between v1 and v2. So that's equal to g of v1 dv plus g of v1 plus dv dv plus g of v1 plus 2 dv dv plus g of v1 plus 3 dv dv, etc. all the way up to g of v2 dv. Now that's an infinite sum of infinitesimal sized spaces, so obviously this is going to be a definite integral. So this probability that our molecule is between speed 1 and speed 2 is going to be the integral from speed 1 to speed 2 of this function g of v with respect to v. And that's going to equal to that ratio we're trying to find, the differential of the number of molecules going speed v divided by the total number of molecules. And it was 1860 that Maxwell first derived this function, capital G of v. Alright, we're going to continue about the distribution function, capital G of v dv. So the requirement is going to be that the definite integral for the entire range is going to have to be equal to 1. Now for speed, remember, it can only be positive. And we're going to ignore the speed of light and so on and just say, okay, all the way from 0 to infinity, the definite integral of g of v dv is going to be equal to 1. Now we're going to get started on the derivation of capital G of v. This is a key function in kinetic molecular theory, so even though it's going to take a long time to derive the whole thing, it's kind of important, so we're going to do it. So the first assumption we're going to make is that the velocity distribution is independent of direction. In other words, x, y, z, diagonal, it doesn't matter. All directions in space are equivalent. Now, we can't ignore gravity, I mentioned a while ago, because gravity is so weak. Now, this is true as long as we have no external field. If you have a magnetic field, electric field, or really strong gravity field, that's going to change a little bit. But we're going to ignore that for now. And then the second assumption we're going to make is that the values of Vy, the speed in y and the speed of z, do not affect the probability associated with the value of the speed of x. which is actually kind of related to 1. We're assuming that they're just totally independent directions, and what happens in one direction has nothing to do with what happens in a different direction. Okay, continuing on chapter 15, section 4, we're trying to derive the distribution function for speed in molecules. So what is the probability that a molecule is going to simultaneously have its x component of velocity in the range of vx to vx plus dvx, and its y component of velocity in the range of vy to vy plus dvy, and its z component of velocity in the range of vz to vz plus dvz? Now remember that spherical shell we're talking about before. If you answer this question, you found 1 point on that shell. Now remember the 2 assumptions we made on the previous slide. The second assumption says that these 2 probabilities are independent for various values of Vx versus Vy or Vz. Now a quick aside about probability and independence. Let's say you have a standard deck of cards. Now the probability of a heart is 13 out of 52 because there are 52 cards and 13 of those are, whatever we said, hearts. And if you can reduce that to 1 over 4. Now the probability of getting a queen is 4 over 52 because there are 52 total cards and 4 of those are queens. And of course this can reduce to 1 over 13. Now those 2 events are independent. Therefore the probabilities can be multiplied. So if we want to know the queen of hearts, we just multiply this 1/4 by 1/13 and we get 1 out of 52. That makes sense because out of 52 cards, there is only 1 queen of hearts. Now, to answer the question we asked on the previous page about x, y, and z, the answer is just lowercase g of the x component of speed times the differential of the x component of speed times g of the y component of speed, or no, this would be velocity, duh. But anyway, times the differential of the y component of velocity, times the function lowercase g of the z component of velocity, times the differential of the z component of velocity. Now remember, these components can be positive, negative, or 0. So remember that capital G of v that we're trying to find, that's our distribution function for speed. But these lowercase g of x component of velocity, g of y component of velocity, lowercase g of z component of velocity, these are distribution functions for velocities. Or multiplied together, it's the distribution function for velocity. Alright, so we're going to label equation 1. So we're talking about g of v, which is for speed, and then lowercase g of v, which is for velocity. So how are we going to reconcile those two? We're going to use the Pythagorean Theorem. So we've shown before that the speed squared is equal to the x component of velocity squared, plus the y component of velocity squared, plus the z component of velocity squared. We're going to call it equation 1 to refer back to it quickly later on. And then we also showed before that we have these probabilities for those x components, lowercase g of v of x, lowercase g of v of y, lowercase g of v of z. They're independent, so we can multiply them. So we're going to call this product phi of v. And this v, remember, is the speed. So we're going to call this equation 2 to refer back to it later on. Now, phi of v is not the same as our g of v. I think I already explained this. Phi of v, this is going to be a point on that shell. And g of v is that whole shell that we want to find. So we're going to take the derivative of 2 with respect to v of x. So we have the derivative with respect to v of x, holding v of y and v of z constant, of g of v of x, g of v of y, g of v of z, and that's equal to the derivative with respect to v of x, of v of y, v of z, of v of v, because we just did the substitution, they're the same thing. Now, we know that the derivative of v of x is just going to be also known as g prime of v of x. I'm sure you'll learn that in Math 251, differential calculus. We're also going to have to use the chain rule because of if v is a function of vx or whatever. So the derivative with respect to the x component of velocity, holding the y component and z component of velocity constant of phi of v, is going to be equal to the differential of phi of v with respect to v times the differential of v with respect to vx. Okay, so that gives us 3. We have g prime of the x component of velocity times g of the y component of velocity times g of the z component of velocity is just equal to the derivative of phi with respect to v, or the derivative of phi of the speed with respect to speed times the derivative of speed with respect to the x component of velocity. Now we want to substitute out this term here. So one thing we're going to do first is we're going to take the differential form of equation 1. So that gives us 2 times the speed times the differential of speed is equal to 2 times the x component of velocity times the differential of the x component of velocity plus 2 times the y component of velocity times the differential of y component of velocity plus 2 times the z component of velocity times the differential of the z component of velocity. Obviously the 2's cancel out, so that just gives us that the velocity times the differential of the speed times the differential of speed is equal to the x component of velocity times the differential of the x component of velocity plus the y component of velocity times the differential of the y component of velocity plus the the z component of velocity times the differential of the z component of velocity. Now remember, we're holding, what's it called? Y and z held constant. So this whole term here, the y component of velocity times the differential of y component of velocity is equal to 0. And likewise, the z component of velocity times the differential of z component of velocity is equal to 0. So all of this just becomes the speed times the differential of speed is equal to the x component of velocity times the differential of the x component of velocity. And then just rearranging using algebra, we have the x component of velocity divided by speed is equal to the differential of speed divided by the x component of velocity. We're going to take this and substitute back into equation 3, which is what we were trying to do. Alright, continuing to trying to drive the Maxwell relation. So now we have equation 4 for future reference. So we have g prime of v of x, this is the x component of velocity, times g of the y component of velocity, times g of the z component of velocity is equal to phi prime of speed times the x component of velocity divided by the total speed, divided by speed. Now we're going to take equation 2 and multiply that by the x component of velocity. That gives us equation 5. So we have the x component of velocity times the g function of x component of velocity times the g function of the y component of velocity times the g function of z component of velocity, and that's equal to the x component of velocity times phi of speed. Now, we're going to take equation 4 and divide it by equation 5. So we have the equation 6 as g prime of the x component of velocity divided by the x component of velocity times the g function of the x component of velocity, and that's equal to 1 over speed times the phi prime of speed divided by phi of speed. Likewise, equation 7, we said that x, y, z, all the directions are arbitrary and the same, they're independent, so we've got the same thing for the y component. We have g prime of the y component of velocity divided by the y component of velocity times the g function of the y component of velocity, and that too is equal to 1 over the speed times phi prime of speed divided by phi of speed. And likewise, equation 8, the g prime of the z component of velocity divided by the z component of velocity and the g function of the z component of velocity, that also has to be equal to 1 over v speed times phi prime of speed divided by phi of speed. Remember, these are all lowercase v for speed. Don't confuse it with capital V for volume. Alright, so now using the previous 3 equations, we have equation 9. So we know that the g prime of the x component of velocity divided by the x component of velocity times g of the v x component of velocity is equal to the y component, or g prime of the y component of velocity divided by the y component of velocity times g of the y component of velocity, which is also equal to g prime of the z component of velocity divided by the z component of velocity times the g of the z component of velocity. We're gonna find that is equal to b. Now b, we know, is independent of these three. The reason is that, well, it's complicated, but basically if these two are equal to b, and it's independent of this, and if it's equal to these two, it's independent of that, it's got to be independent of all three. More importantly, though, we know that b is a constant, because if b is independent of this, and b is independent of this, and independent of that, the only way it can be equal to each other is if they're constant. Now, we're going to multiply it by b. So we have b times the x component of velocity is equal to g prime of x component of velocity divided by the g of the x component of velocity. Using the substitution we did before, then we have dg divided by dvx divided by g. So that is equal to dg divided by g times d of v of x. Just rearranging that then, we have dg divided by g is equal to b times vx dvx. We want to integrate that, so we have the integral of the differential of our g function divided by our g function is equal to the integral of that constant b times the x component of velocity times the differential of the x component of velocity. Alright, so that integral gives us the natural log of this g function is equal to 1/2 times that b constant times the x component of velocity squared plus c, where c for now is just any integration constant. We've got to determine later. So taking e to both sides then and doing a little arithmetic, we have g is equal to e to the 1/2 times that vx squared times e to the c, and we're going to define a new constant, capital A, as this equal to e to the c. So now we have g is equal to a times e to the 1/2 b vx squared. And this is our g function for v of x or v of y or v of z. But we still have to determine what are the values or functions or whatever of a and b. So lowercase, excuse me, lowercase g of the x component of velocity times the lowercase g of the y component of velocity times the lowercase g of the z component of velocity is equal to phi of the speed, remember. Substituting all that in then we have a times e to the 1/2 b vx squared times a times e to the 1/2 b vy squared times a times e to the 1/2 b vz squared. And then we can simplify that. Okay, a cubed equals e to the 1/2 b. Combine all those two, we get vx squared plus vy squared plus vc squared. Remember, v squared plus vy squared plus vz squared is equal to v squared. Therefore, all that is just equal to a cubed times e to the 1/2 bv squared. And that is our function phi of speed. Now remember, before we had the capital G, probability distribution function, we said the integral from 0 to infinity must be equal to 1. Likewise, for x component, y component, z component, they can be positive or negative. So our definite integral is going to go all the way from negative infinity to positive infinity. But it's still true. If it's a probability distribution function, the definite integral of that entire domain must be equal to 1. Alright, so we pull out the constant a times the integral from minus infinity to infinity of e to the 1/2 b vx squared dvx equal to 1. Now, this constant here, b, it has to be less than 0. If it was greater than 1, this integral would go to infinity, so you couldn't set it equal to 1. This definite integral wouldn't exist. Like I said, it would go to infinity. So now we know not only that b is a constant, but b is less than 0. Now what we're going to do is we're going to say, okay, let's have minus a equal to 1/2 b. So we have e equals minus b over 2. The reason is we need to evaluate this integral in a table of integrals. Now we know the integral all the way from minus infinity of x to the 2n e to the minus ax squared dx, that's equal to 2 times the integral from 0 to infinity of x to the 2n e to the minus ax squared dx. That's just because the two sides are symmetric, so adding both sides is twice either one side. Now, we know in this case a is greater than 0, and for what we're doing n equals 0. So we're going to use our dummy variable x instead. So we have x squared is equal to vx squared, so it'll match this format up here. And then dx is equal to dvx, again, just so it'll match this format up here. So we can evaluate this integral. So now what we have is that 2a times the integral from 0 to infinity of e to the 1/2 bvx squared dvx is equal to 1. So, or the integral from 0 to infinity of e to the minus ax squared is equal to the square root of pi divided by 2 times the square root of a. Okay, so now, thanks to that table of integrals, we know that 2 times this capital A of the integral from 0 to infinity of e to the 1/2 b times vx squared dvx is equal to 2 times this capital A pi square root of pi over 2 times minus b over 2 to the square root, 1/2, equals 1. That's a Gaussian integral. We're going to solve this for a. So we get a times the square root of pi divided by minus b over 2 is equal to 1. Or that gives us a times the square root of 2 pi over minus b. Oops, that should be equal to 1 still. So that just gives us that a is equal to the square root of minus b divided by 2 pi. So putting that back in where we had a before, we have the g function of our x component of velocity is equal to this minus b over 2 pi, all that to the square root, times e to the 1/2 times that b, same b again, times the x component of velocity squared. So now we only have one variable we need to find. We got rid of a, but we still got to figure out what is this lowercase b. Now remember, the average speed squared is equal to 3 times the average x component of velocity squared. And the average energy of translation for one molecule is equal to 3/2 times kT. Remember, k is the Boltzmann constant. I mentioned that before. And likewise, the average energy of translation, again for one molecule, is equal to 1/2 times the mass of that molecule times the average speed of that molecule squared. Okay, so by transitivity of equality, now we can say that 3/2 kT is equal to 3/2 m x component of velocity squared. That's average, remember. So that gives us equation 10, that the average x component of velocity squared is equal to the Boltzmann constant times the absolute temperature divided by the mass of one molecule. Now let's say that we have a continuous variable w, such as speed. But we're going to leave it w for now because it could be anything. So if we have this g of w is the distribution function for w, then the g of w, d of w, is the probability that w lies between w and w plus dw. We already talked about that before when we talked about the x component of speed and so on. So if the average f function of w is going to be the integral from the minimum of w to the maximum of w, of this function of w times the probability, or the GW dW. Now remember, if you have the average of f1 of w plus f2 of w, that is equal to the average f1 of w plus the average f2 of w. On the other hand, if you have the average of f1 of w times the average f2 of w, that is not the same as the average f1 of w times the average f2 of w. Okay, another rule for averages is if you have the average of a constant times your function of w, you can pull the constant out just like you do with integrals, and you have the constant times the average of the function of w. Now we need to find our average x component of velocity squared is equal to what? Well, we know our x component of velocity, that's going to be equal to our w, the continuous variable. Our function of w is vx squared, the x component of velocity squared. Our minimum is going to be minus infinity, because remember, component can be positive or negative. And our maximum for the w is going to be positive infinity. So that gives us the average x component of velocity squared is equal to the integral, definite integral, from minus infinity to infinity of the x component of velocity squared times this g of x dv of x. This is our probability, remember, of each of these. So we're going to substitute in for g of v of x, and we're going to use our table of integrals to figure out exactly what this is. So the average x component of velocity squared is equal to the integral from minus negative infinity to positive infinity of vx squared times b over 2 pi to the 1/2 times e to the 1/2 b vx squared dvx. Now we can pull the constants out, so we get our average x component of velocity squared is equal to 2 times minus b over 2 pi to the 1/2 times the integral from 0 to infinity of x squared e to the 1/2 bx squared dx. We're just using x as a dummy variable, so we can use the table of integrals to figure out what this is equal to. So our average vx squared is equal to 2 times this minus b over 2 pi to the 1/2, our same constant, and the integral, according to the table of integrals, is equal to 2 factorial over, or times pi to the 1/2, divided by 2 to the 3rd power, times 1 factorial, times minus b over 2 to the 3/2. And all this simplifies to just 1 over minus b. Alright, so that we showed in the previous slide that the average x component of velocity squared is just equal to minus 1 divided by that constant b. And we also know that the average x component of velocity squared is equal to kt over m. So we know that b is equal to minus kt over m. Remember, m is the mass of one molecule, k is the Boltzmann constant, and t is the temperature, which has to be an absolute temperature, obviously. So we have g of v of x is equal to m over 2 pi kt to the square root power, or to the 1/2 power, square root of all this, times e to the minus m, x component of velocity squared, divided by 2 kt. And that is equal to this fraction 1 over n times the differential of the number of molecules with x component of velocity divided by differential of x component of velocity. Now the constant t, this whole thing, m over 2 pi k to the square root, is constant. And we know k is equal to 1.38 times 10 to the minus 23rd joules per Kelvin. So this product, k times t, has units of energy. This kt is the characteristic energy of the system. Now we remember this whole time we were trying to find capital G of v dv. We can say that it's proportional to lowercase g of v of x times lowercase g of v of y times lowercase g of v of z times the differential of x component of velocity times the differential of the y component of velocity times the differential of the z component of velocity. Alright, so let's say we have that same velocity space I drew at the beginning of this section, where you have the sphere within a sphere, and each location in 3D space is a velocity. So this dvx times dvy times dvz, so the differential of the x component of velocity times the differential of the y component of velocity times the differential of the z component of velocity, is a volume element within this velocity space. So here's my sphere within a sphere, and all within this shell, we've got all these little cubes. Each one of these cubes has dimension dvx times dvy times dvz. Now the radius of the inner shell is our initial velocity, and then the radius, the outer shell, is just v plus dv. Now we want to find this shaded volume, the entire sphere. All these cubes added up, basically. It's an integral. Now we know the volume of the larger sphere is 4/3 pi times v plus dv cubed, and we know that the volume of the smaller sphere is 4/3 pi times v cubed. So the shaded region must be the difference between those two. So it's 4/3 pi times v plus dv cubed minus 4/3 pi times v cubed. Okay, so doing some arithmetic here, that shaded volume is equal to 4/3 pi times the speed squared times 3 times the speed squared times the differential of speed, plus 3 times the speed times the differential of speed squared, plus the differential of speed cubed, minus 4/3 times pi times the speed cubed. doing canceling out the like terms or whatever you call it. So 4/3 pi is times 3 times the speed squared times the differential of speed plus 4/3 pi times 3 times the speed times the differential of speed squared plus 4/3 pi times the differential of speed cubed. Now we're going to neglect the second and third terms because they're small. So what that is going to mean is that our volume, that entire shell, is equal to 4 times pi times the speed squared times the differential of speed. Remember, this is capital V for volume, this is lowercase v for speed. And this whole sphere, this is called our volume element. So the reason is, remember, in that entire shell, all the different points, they have different velocities, but they all have the same speed. So this shell tells you all those different points that have the exact same speed. So g of v dv, remember this is the capital G function we were looking for the whole time, is the sum over that shell of all these different points that have the same velocity. So we have our same speed. So we have m over 2 pi kt to the 3 halves, because remember 3 dimensions x, y, z, times e to the minus m vx squared plus vy squared plus vz squared over 2 pi, or 2 kt, times the differential of vx, differential of y component of velocity, and the differential of z component of velocity. So we have the capital G of speed times the differential of speed is equal to m over 2 pi kt to the 3 halves times e to the minus mv squared, our speed squared, over 2 pi, or 2 kt, times that volume we found out. We just substituted it right in, and we get 4 pi v squared dv. Just remember, I mentioned this before, lowercase g of x component velocity, and that's a distribution function for velocity. Now our capital G of v that we just found, that's our distribution function for speed, which is what we want. So this is what the function actually looks like for lowercase g of v of x, the x component of velocity. And it's in the format just general a is equal to e to the minus a vx squared. So this is what we call a Gaussian function, or a normal function. If you had probability, you know what that means. So we have our horizontal axes and velocity, 0 in the middle, positive 50,000 centimeters a second here, negative 50,000 centimeters a second here. Now for a temperature of 300 Kelvin, which is roughly room temperature, so you have the peak up here, and then it goes down equally on both sides and curves down. Higher temperature, 1000 kelvins, the peak is lower, but it goes out wider. Now, the vertical axis, we've taken g of v of x, and then we've divided by seconds per centimeter, so the vertical axis is technically dimensionless, but it doesn't matter. This is just to give you the shape, idea of the shape. Now, both of these curves, they have the same area underneath. In fact, hopefully you realize the area underneath is 1. That's how we found the curves in the first place. Now, the higher temperature curve, as you can see, it doesn't peak as high, which means there's less molecule at low speed, but it's wider, which means there's more molecules at higher velocity. Well, higher speeds, higher plus and higher minus. Now, you notice the most probable velocity for any temperature is 0, but obviously that doesn't mean that nothing is moving. Okay, so this is what a capital G of v looks like. Remember, g is a function of speed, which can only be positive. So we start at the origin now. So for a lower temperature, like 300 kelvins, room temperature, it goes up, levels out, comes back down. For a higher temperature, like 1000 kelvins, it'll go up, not as much. It'll peak at a higher speed, and then it'll level out. So this is in centimeters per second, so room temperature, guess we get average, or about most probable. The peak here, the top of this curve, this is the most probable speed. I didn't draw it very well, I sort of eyeballed it. But as you can see, for the higher temperature, you've got a higher, most probable speed. Alright, here we go. Finally, the end of section 4 in chapter 15 of physical chemistry. So here's another way of looking at our capital G function of speed. So for argon, a heavier element, we have the peak at a lower speed and it curves down like this. For a not so heavy element like neon, it goes up, curves at a higher speed, and then comes back down. And then of course for a really light element like helium, it curves up, it peaks at a much higher speed, and then it comes back down. Remember, the mass of argon is 40, the mass of neon is 20, and the mass of helium is 40. So this also makes sense even if you didn't know the distribution, because your average speed squared is equal to 3 kT over m, or 3 RT over m. Notice the m is on the bottom, therefore bigger number is going to give you a smaller speed. Or no, yeah, a bigger number is going to give you a smaller speed, and the smaller number will give you a bigger speed.